Welcome to Math 104, Chapter 5.3, Exponential and Logarithmic Equations. We are working today on how to solve one another. Make sure your foundations on Chapter 5.1 and 5.2 are solid in order to move forward. So first, we're going to start by rewriting the equation with the term containing the exponential or the logarithm by itself on one side. Now, if they are not by themselves, if the exponential is not by itself, then we're going to have to make do an extra step. Now, let's take a look at the below. Locate, well, first determine, do you have an exponential or a logarithm? And then locate it. Well, notice that we do have an exponential over here. We have a base 10 raised to the 4t. Now, is your exponential term all alone on one side? No. So if it is not alone, notice what is technically this 150. This is the coefficient of the term. So if you have a coefficient, we are going to divide both sides by the coefficient of the term containing the exponential or the logarithm. So let's go ahead and divide that out. 150, 150. So then we get 20 is equal to 10 4t. Okay. Let's change your new equation now. If we now have your exponential all alone, let's change it to a logarithm. Or if you have a logarithm, let's change it into the exponential. So we're going to be changing these to the opposite form. So if we have an exponential, we make it into a logarithm, or if we have a logarithm, we make it into an exponential. Now, why do we want to do this? Well, keep in mind, we are trying to solve for t and get t alone. Can this 20 really have a base of 10? No, so we can't do it that way. So instead, we need to transform it into a logarithm and throw it into your calculator. So how do we get this 10 to drop its exponent? Well, we worked on it previously in chapter 5.2. We said we can actually take the log of the same base. If we take the log of the same base, they are going to cancel one another out and allow your exponent to drop. But what you do to one side, you need to do to the other. So we're going to take the log of 10 on both sides. So now you're left with log 10 of 20 is equal to 4t. Now we get to solve for your variable. So let's try and solve for t. The last thing we need to do, we'll get t is equal to log base 10 of 20 divided by 4. Now we are not able to divide 20 by 4 because this log base 10 of 20 is a number. Notice how much different they come out to be. If we do, let's see, log base 10 of 20, this is our number over here, right? 1.3 versus if we were to do log base 10 of 20 divided by 4, right? So notice that log 20, if you were to do it on the other side first, it comes out with a number. The second is not accurate. Instead, we are dividing this whole thing by 4. Now this is called your approximate solution. Your rounded solution, your estimated solution, whereas this value here is your exact solution. Exact meaning we need a calculator to give us what this value is. So punching it into your calculator is always going to be that exact solution form. Now we can confirm to graph it. So notice that we have two sides of the equal sign, which we haven't dealt with in quite a while, which means we're going to put this both on opposite. We're going to put them on the y equals. So we have y equals, we said 3,000. That was one of your y's. And your other y, we said y equals 150 times 10 raised to the 4t. Close your parentheses. Now we might need to change your window a little bit because we're trying to find where they intersect, right? Notice that where y is equal to 3,000 is huge, and our x values and your y value actually does not go all the way that high. So we're going to have to change it a little bit. Instead of saying 3,000, we're at the very tippity top. There we go, 3,000. You can see kind of the start of a red line. So let's get further above, let's say 9,000. Well, 9,000 is a little much. Let's say 7,000. If you wanted to change your steps, feel free to go ahead, but we're really just looking for where they intersect, which they're going to be intersecting at 0.325. And notice that that is your answer. You can do the same thing in your TI-84s just by putting both of your equations in and hitting second trace intersect. But make sure you see the intersection first by playing with your window. Now let's take a look over here. Radioactive carbon-14 decay has this following equation. In T is in years, to find the age of the fossil, if the original amount was 1,000 grams, the present is 1 gram. Find the age and graph to verify the findings. Okay, so first thing we want to just recognize is the difference between y and y naught. Y naught or y sub 0 is really your initial value, your starting value, your original value, and y is just your end value after t time. So in our case, what is going to be your present value, your initial value? Well, we're being told your initial original value was 1,000 grams. So we can go ahead and replace your y naught, your y sub 0 to be 1,000. And then your end value, we said at the end, I want it to be 1 gram. So then we're looking forward to finding the age. So we are taking the same exact approach, the same exact steps as the one before it. So if we have 1,000 in the way, we need to then divide both sides by 1,000. So you have 1 over 1,000. If you wanted to put that into a decimal form, feel free. Okay, so now we have your exponential all alone to one side. So how do we get rid of an exponential with an e? Well, back in chapter 5.2, we said e is special. It has a reverse logarithm called a natural log. So we're going to be taking the natural log of e to both sides. That way, your e's cancel and your exponent drops. So you have ln, if you wanted to keep writing your e, that's all right. 1 over 1,000 is equal to negative 0.00012t. Then we can go ahead and divide. So your exact solution is ln of 1 over 1,000 all over negative 0.00012. That's your exact. Your approximated value, let's go ahead and punch that in. So we're going to take function, we're going to do ln We said 1 divided by 1,000 all over negative 0.12. So we should get 57564 and some change. Now, what does this actually mean? So see if you can actually bring meaning to the context of your answer. So if we're talking about radioactive carbon-14 decay and we want to find the age of the fossil, we can say the fossil is 57,564 years old, given that its initial gram was 1,000 and now its present gram is 1. Now your what is it called? Yours you guys are not WebAssign, you guys are Pearson. Pearson actually might be very picky. Notice that after 6.4, we have 0.6. That is actually going to round your answer up. So actually, we are not in 64. We're actually well into year 65. So let's go ahead and change that answer. We are now in the year 65. So it might have come up a few times on your homework where it's saying that it's wrong. We're rounding up into your year because we are in the year 64 or at the very end. So 5654. But then we have a little bit that we're now trickling into the next year. So round up. We can go ahead and graph the finding as well by putting them onto both sides of the equation. I'll do this one in your TI-84. So we have one side is 1 gram, the other side is 1,000 E negative T. Okay. So if we hit graph, we do see our line here. Now keep in mind what our answer came out to be. It was very, very big for your years. So we also know your initial finding, your initial value for your y was 1,000. So our max is only going to 10, so we want to get above. So let's try and sandwich your initial value between 2,000 and perhaps negative 1,000. Your initial value was the 1,000 value. We want to make sure that it's well in between your parameters. And notice that there is a big difference between negative 1,000 and 2,000. So let's go ahead and change that scale to be a little bit more generous. Now for your T, and let's see how that changes your window. Well, notice that you now can see two lines, which is great. We want to figure out where do they intersect. So we need to change your window. Now we don't really need any sort of negative values. And instead, we want to get a little further out. So by this point, let's try 500. There's a big difference between 0 and 500, so maybe we go up by 20. We are starting to see where your red line is dipping down, so that's a great indication. Now to speed this up, we know your X value, your time is very large. So let's go ahead and see that change where we can see it getting very close. And one more time, let's do this, 70,000. Oops, there you go. All right, so at this point, let's go ahead and hit second trace. We're gonna assume that there is some sort of intersection. So the left bound, to play it safe, you can definitely tell that this is not intersecting right here, and we can kind of assume it's not intersecting here. Whereas the remainder, we definitely want to make sure that we are far enough away from where we assume the intersection is. And then you can hit enter and notice that it's going to spit out your answer at the very top. Okay, so I would say pause the remaining lecture and see if you can do the following on your own. So $10,000 is invested for Y years at 10% compounded annually, and it's giving us the equation. In how many years will the investment grow to 45,950? So those are our two sides of the equal sign. I would definitely get practice doing this by hand and then again by the calculator. So let's go ahead and divide. Let's go ahead and write the log of the same base. That'll go ahead and cancel and drop. And there you go, where t is roughly 16. If you haven't seen the change of base before, let's try it one more time on our TI-80 because we have 1.1, we have 4.595, or if you wanted, you can do the change of base formula. Perhaps you don't have the fancy button. So we're going to divide that value by this value. And notice it comes up with the exact same. All right, to make sure you can try it graphically as well. Now let's solve it in an from a logarithm into an exponential. So is your logarithm all alone? No, it is not. So let's go ahead and divide. Oops. So you have log 3 of x is equal to -2. Now, how do we go from a log to an exponential? Well, we're going to be looking at a base of 3, so which means we're going to be writing a base of 3 as well. That will allow us to cancel this and allow your x to drop. 3 to the -2, which means we have 1 over 3 squared, which is 1 over 9. We want to make sure that any sort of negative exponent, we then drop back into the denominator. Let's try it one more time here. So is your natural log all alone? No, it is actually twofold. We don't want to divide by your coefficient yet unless you're willing to divide all of your values by 3. Otherwise, we can go ahead and subtract the 6 to get 6 and then go ahead and divide. How do we get rid of your natural log? Well, the base of your natural log is e, so by writing an e to both sides, it will allow us to cancel. So then we get x is equal to e squared, which we can leave it as we're seeing it here. We already talked about doing it graphically. I'll show you graphically over here. Let's take number 4. We have 4 log 3 of x. Nope, that's the right one. And then we'll have to do the change of base. Oh, actually, I don't think it's going to allow us to do it. Oh, functions? Oh, there we go. Oh, there we go. 4 log 3 of, oh no, what was it? Of x. And then we have y equals -8. I believe it's -8. Yes. Okay, let's reset everything. Okay. All right, so we do have some sort of an intersection going on, which means we are not, we want to actually make sure we see your y value, which your y2, the second y, is equal to -8. And if I'm not seeing it here, let's just change your y. Let's do a good sandwich. So let's do -15. And there you see the intersection. So that intersection is 0.111, which happens to be the same value as 1/9. Okay, that should be it. Make sure you just pick whether you want to do it graphically or by hand. We can also try to do the swoop method. I'll do the swoop method on one of these if you are if you have picked doing the swoop rather than writing the log or exponential. So for those who like the swoop method, I'm just going to back up over here where we had 20 is equal to 10 to the 4t. And that swoop method we talked about goes from your base up and around to your exponent, where we now need to remember to write a log of your base. 20 is equal to 4t. And then continue as normal. Let's try it again one more time over here, where we have 1/1000 is equal to e to the negative 0.00012t. Okay, so we are swooping one more time. So writing your log, in our case, we need the natural log to be written down in order to have e. And one more time below. I'll do it over here. 4.4, nope, 595, 1.10 t. Okay, don't forget to swoop. And then we have to write log of 1.10, 4.595 is equal to t. I'm going to do a few more over here. If we were to do it on this side, we have log 3x is equal to -2. We're going to start at your base and swoop around. Now we just write your base, your 2 is equal to x. Last one, we said ln of x is equal to 2. Start on your base, come up and around, and land on x. E to the 2 is equal to x. So if you like the swoop method, keep trying that. If you like the graphical method, please do that as well.